Hello class, this is CSE-5720, Section 2, Week 9, Fall 2025. So we began our discussion on relational algebra last week, and we began with 2 of the 6 fundamental operations. So it turns out that these 6 operations are fundamental to relational algebra. Nearly every query you can ever think of in SQL can be expressed using just these 6 operations. And I'll show you why that is, but that'll be for a little bit later. We began with 2 of those fundamental operations. They were select and project. So, select selects tuples that satisfy a given predicate. So, department name equals physics for a relation. Well, this is the instructor relation. Basically, pick out the tuples for which this predicate, department name equals physics, is satisfied. And there we go. We just found all the physics instructors. We can build up larger predicates using comparison operations. No. We build up predicates by comparing an attribute with another attribute or an attribute to a value using one of those 6 comparison operations. We can build up larger predicates by using the logical connectives and, or, and not. The select operation, denoted using lowercase sigma, corresponds to the where clause of a typical SQL query. The from clause just specifies what table we're working with. So, if the selected clause does not correspond to sigma, and rather it's where, what does select correspond to? It corresponds to project, denoted with a capital Pi, though I've seen some contexts use lowercase pi instead. You personally might be more familiar with the capital sigma, used to denote summations. The only other place I can think of where you may have seen a lowercase sigma is statistics for standard deviation. If you're lucky, you may have also seen a capital Pi. That means multiplication of a sequence of numbers. Much like how summation is just addition of a sequence of numbers. But here we are dealing with lowercase sigma and capital Pi, representing respectively selection and projection. Or select and project, I should say. So project just selects the columns of a relation. It's like the attributes of a relation. So select ID named salary from instructor. That's just gonna return a relation that consists of all the attributes in the instructor relation, except for the department name, because there were 4 attributes in instructor: ID name, salary, and department name. That just gives us a table that is more useful for payroll workers. And there we go. And we've also seen an example of how you can convert a query into an equivalent expression using relational algebra. So we take this example query, evaluate it in the order of from, where, select. The from clause tells us we're working with the instructor relation. The where clause tells us we're going to pass it into sigma, and the predicate is department name equals physics. Then we take that expression, because this is an expression already, and we're going to build up a larger expression by passing this expression into pi. So pi subname of sigma subdepartment name equals physics of instructor. So pi of sigma of instructor. And there we go. This query on the left here is equivalent to this expression on the right here. Okay, so that is 2 of 6 operations. Let's look at the union operation. So the union operation, if you're familiar with set theory, it's going to be exactly the same notation. So in SQL, there are 2 queries that we've seen that we used to first demonstrate the union operation keyword. And it was these 2 queries. The first one is find all courses that take place in fall 2009. And the other one is find all courses that take place in spring 2010. If we want to find the union of those two sets, we would put the keyword union in between those two queries. Oh, and the equivalent relational algebra expressions are down here. So if we want to find the union of these two queries, we would add the union keyword between them. If we want to find the union of these two expressions, we put the union symbol between them. There are a few rules to keep in mind. The use of the union symbol is valid, but only if these two rules are satisfied. The two sets R and S must have the same arity. That is, that they have the same number of attributes. But also, their attributes must have their corresponding attributes must have the same domain. So the domain of the ith attribute of R and S must be the same. So these two queries have a course ID attribute. So their domains must be, well, all the course IDs. The two also have the same semester attribute, so they must also have the same domain of fall, spring, winter, summer. And the year, they must also have the same domain, which is, in this particular database example, it is defined as the years between like 1750 whatever to 2100. So if we have the same attributes, the same number of attributes, and all those attributes and the corresponding attributes have the same domain, it is then valid to find the union of these two expressions. The same is true for set difference. So set difference is the set of all objects in the first set that don't appear in the second set. So set difference is denoted with a minus sign. If we did set difference with these two queries, we would find the set of all classes that take place in one semester that do not take place in the other semester. In other words, we just found all the classes that take place exclusively in fall, and since set difference is not commutative, if we swap the order, we get the set of all classes that take place in spring. So, in one ordering, we get the set of all classes that take place in fall, exclusively in fall. And if we switch the order around, we get the set of all classes that take place exclusively in spring. Cartesian product. So this is the operation where we take rows from two different tables and produce every possible combination that can exist. When queries are performed on multiple relations, we're not gonna consider natural join for now. We conceptualize the query as being performed on the Cartesian product of those relations. And we denote Cartesian product using the cross operator. And here's an example of one such query. Select name and course ID from instructor and teachers, where instructor ID equals teacher's ID. So, if we want to rewrite this expression using relational algebra, from what instructor comma teachers tells us we're doing the Cartesian join of instructor and teachers. The where clause tells us we are passing this into sigma, where the predicate is instructor ID equals teacher's ID. And the select clause tells us we're going to pass this expression into pi, where the attributes being selected are name and course ID. There we go. And like how in math you can have an expression rewritten like how in math you can have an expression that can be written in more than one way, so too can you have a relational algebra expression written in more than one way. Two such expressions are equivalent if they provide the same result. So these two examples are equivalent if they provide the same result. So that is 5 of the 6 operations already. We have select, project, union, set difference, and Cartesian product. The last one is rename. We denote that using a lowercase rho. It looks like a P, but That is the Greek letter. That is the equivalent Greek equivalent of the letter R. Given an expression E, it's going to rename the result of that expression under the name of X. So rho sub X of E just returns that expression, or rather the result of that expression, with the name of X. We can also rename individual attributes too. So, this is the end of part 1 for chapter 6.1. There is another set of slides that gets more into the details of what else we can do with relational algebra. However, it is extensions to relational algebra that, for the most part, make it easier to use. We're also going to look at an example of how you would use the rename operation in practice. Okay, switching to the other set of slides. Okay, so let's demonstrate the rename operation. So let's consider the following query. Find the highest salary in the university. So normally I think we could just use some aggregate function and then just find the highest value in the table. But there is one way to do this that demonstrates the use of the rename operation. And that strategy is as follows. Step 1. Compute a temporary relation that consists of all the salaries in Instructor that are not the highest salary. So we find everything that isn't the highest salary. But if we take that and perform a set difference between the original relation and this temporary relation from step 1, if we do a set difference, that's going to give us the highest salary. Right, so how do we compute step 1? Well, we're going to start with the Instructor relation. We want to compare the values of all salaries, but for this to work, we're actually going to compare Instructor with itself. But the problem is there would be two salary attributes, so we want to rename one of them. In other words, we need two copies of the Instructor relation. And we want to compare one salary with the other. And to make sure we can do that without mixing up the two, we're going to rename one of those relations to D. And now we can proceed with our Cartesian product. So this is going to get a little bit crazy. But it's going to combine every tuple with itself in every possible way. So we have this row, for example, 10101 Srinivasan, computer science, salary 65,000, and then 4 more attributes that are the same values. And then Wu, and then Srinivasan's information. Mozart, and then Srinivasan's information. This looks like a mess, but bear with me here. We have combined tuples from the Instructor relation with itself in every possible way. But now with this, oh, by the way, the full attribute name for this, it should be Instructor.attribute name and D.attribute name. I ran out of room here. But yeah, that should be the full attribute name. Anyway, if I can reassemble the video. There we go. Okay. Now we have the Cartesian product of Instructor with a copy of itself. Let's select tuples where Instructor.salary is greater than D.salary. So, is Srinivasan's salary greater than itself? No. Is Wu's salary greater than Srinivasan's salary? Yes, so we'd select that. Is Mozart's salary greater than that? No. Is Einstein's salary greater? Yes. Is Al Said's salary greater? No. Is Gold's salary greater? Yes. So we select all those tuples for which the first salary is greater than the second salary. And once we have that, all we gotta do is we just project instructor.salary. So this is gonna whittle down this entire relation so that all we have left is this salary column here. We selected all the rows and we selected all the columns that we need for our relation, for our output relation for step 1. So this is computing the first step in finding the largest salary in the instructor relation. You might be thinking to yourself, how is this supposed to compute the largest salary? Well, here's the thing. It doesn't. It finds everything else except for the largest salary. So somewhere in this table, we are comparing the largest salary with itself. But you can just eyeball this and then determine that it's Einstein's salary that's going to be the highest of them all. But is it greater than itself? We are comparing the largest salary with itself. Is it greater than itself? No. Because by definition, A is greater than A is going to be false. Because how can something be greater than itself? So that means this is not selected. But that also means that all other salaries that isn't the largest salary have been selected. So if we add this back with the rest of our Cartesian product here and show which rows are going to be selected, now what we have is all salaries being selected that isn't the largest salary. And there we go. We have all the salaries that isn't the largest salary. Oh, by the way, you might be wondering, there were several salaries that were duplicates. And for simplification processes, this is just from the definition of a set. A set disallows duplicates. So there were going to be some... Actually, no, there weren't going to be any duplicates in this particular Cartesian product, but there were going to be some duplicates when we projected the salary attribute. So for our purposes, we just eliminated the duplicates just from the definition of a set. A set disallows duplicates. Okay, so now we have the set of all salaries that isn't the largest salary. Now we can bring back another copy of the instructor relation, project just the salary, so now we have a relation consisting of all the salaries. If we do a set difference between this relation on the left and this relation on the right, set difference says find the set of all objects that are in one set that are not in the other set. So we did the set difference of these two, because this one contains everything but the largest salary, and this contains everything and the largest salary. If we did a set difference between these two, we're just going to get the largest salary back. There we go. So this expression demonstrates how you can use the rename operation. Though there is an alternative that the author does not use, because he argues that it's easier to go by the names of attributes rather than the position in which they appear. This query down here is an alternative of writing the same query, except we are using positional notation, where the $4 means the fourth attribute of the Cartesian product of instructor and itself. Because instructor.salary is the fourth attribute, and instructor cross instructor has 8 attributes, the 8th attribute is also a copy of the salary. So what this is saying is, compare the value of the 4th attribute with the value of the 8th attribute. Select it if the value of the 4th attribute is greater than the value of the 8th attribute. And then this one says, just select the fourth attribute. This is another way of writing the same query that does not use the rename operation. It's just an alternative that you probably might like to know, just in case you like this notation better. And just like that, we have all 6 operations in relational algebra. So, let's look at the definition of that. The definition of relational algebra. So, there are 6 fundamental operations, and there are expressions. A general expression E is built using any of the 6 operations, each one operating on 1 or 2 sub-expressions, E1, and if it's unary, and E2, and also E2 if it's binary. The most basic expressions are going to be of one of 2 forms, a relation in a database or a constant relation that I'll have to show you what that means in a little bit. So, expressions are built off of smaller expressions, which themselves are built from even smaller expressions. So, the further down you get, you're eventually going to get down to the smallest possible expression, and that's the 2 basic forms of an expression, a relation in a database or a constant relation. So, your basic expressions is going to be one of those 2 forms. A constant relation is just a listing of tuples enclosed in curly brackets. So, any 2 of those are going to be an expression that you use to build up larger expressions by using any of the 6 fundamental operations. There we go. So we have E1 union E2, E1 set difference E2, E1 Cartesian product E2. Those are your 3 binary operations, and then your 3 unary operations are sigma p of E1, pi s of E1, or rho x of E1, where p is a predicate, s is a list of attributes from E1, and x is the name we would like to rename the result of E1 to. And we can express any query in SQL using only those 6 operations. Let's talk about a few additional operations that we would like to have that makes working with relational algebra a little easier. So, these 6 operations are fundamental. They can express any relational algebra query. But we would like to add a few more operations just for our convenience. Such as, hey, we have the union operation, where's intersect? Well, if you've taken set theory in the past, you'll recall that the intersection of 2 sets, A and B, that's just a set of objects that are present in both sets. So we have 2 sets A and B with random objects. A intersect B, it's this purple smiley face here. If we can find a way to express A intersect B using only just the 6 fundamental operations of relational algebra, we can define it as an additional operation that we can use in addition to those fundamental operations. So let's consider the set difference of A and B. That's the set of objects that are in A that are not in B. So the smiley face is in both sets. And the set difference A minus B, it's just going to be this orange diamond and this green, what is this, a clump of broccoli? Anyway, so that's the difference, the set difference of A and B. But what if we did the set difference between A and A minus B? Well, that's going to be the set of objects that are in A that are not in A minus B. So we have the orange diamond in both sets, and we have the green wad of gum, I guess, in both sets. That means the set difference of A and A minus B is going to be the purple smiley face. But hey, that's the same as A intersect B. We need to write it as A minus, and then in parentheses, A minus B. because set difference is not associative. If you did instead A minus A, and then enclose that in parentheses, you get the empty set, which is not what we want. So set difference is not associative, so that we must specify that these parentheses go here and not. The parentheses enclose A minus B, not A minus A, because set difference is not associative. But it means, once we have that, we have the definition of A intersect B as this purple smiley face, but using only set difference, we managed to define the same thing. So now, we have set difference defined, we can use that as an additional operation. This does not make relational algebra any more powerful, it just makes it easier to use. So here is our definition as it pertains to relations R and S. So it's R minus S. So now we have set intersection. We can use that alongside our union operation. Okay. Now we have all three set operations represented. Union, intersect, and set difference. There's another one that we would like to add, and that is natural join. We've encountered natural join earlier on in the course. It's a little bit tricky to define, so let's just start with the definition and go up from there. Whoa, what is that? Well, if you ignore all the subscript text for a moment, it's just pi of sigma of R Cartesian join S. So, there's also a big R and big S, so what's that? So, little r and little s are relations. Big R and big S, those are the sets of attributes for R and S respectively. All attributes A sub I belong in the set R intersect S. So, all of these attributes A sub 1, A sub 2, all the way to A sub n, those are just the attributes that R and S have in common. This means R intersect S, that is a set of attributes that R and S have in common. R union S, that's going to be all the attributes. That's going to be all the attributes between R and S without duplicates. When we perform the Cartesian join of little r and little s, and they have some attributes, m attributes for R and n attributes for S, we get a relation that's going to have m plus n attributes. But some of those attributes are going to be the same. So the natural join of R and S will typically have fewer attributes. So the natural join of R and S will typically have fewer attributes than the Cartesian join of R and S, and that's because some of the attributes are literally the same. So, if R and S have at least one attribute in common, then R intersect S will have at least one common attribute. It also means that R union S will have fewer attributes than the number of attributes of R, little r, Cartesian join, little s. Is this all making sense? Anyway, let's go inside this expression and evaluate it inside out. So R cross S, that's just a Cartesian join of the relations R and S. All this stuff, as subscript text to sigma, that is comparing tuples for which the common attributes for every common attribute that appears in R and S, it's going to select those tuples for which R sub A1 equals S sub R dot A1 equals S dot A1 and R dot A2 equals S dot A2 all the way to R dot AN equals S dot AN. Because when we perform a natural join, we combine tuples based on whether they have the same value for a common attribute. In other words, a natural join is just a subset of a Cartesian join. in a way. We're just selecting the rows for which the common attributes have the same value. And I talked quite a lot about R union S. That is a set of all attributes between relations R and S. And this is big R and big S, which represents the attribute sets of little r and little s. So when you do a Cartesian join between little r and little s, you're going to have m plus n attributes. If you did the natural join of r and s instead, you're going to have fewer attributes than if you did r Cartesian join s, which means that r union s, big R union big S, is going to have fewer attributes than the number of attributes in little r cross little s. Which is what all this other stuff here is trying to say. When we perform a natural join between R and S, both attributes typically have at least one attribute in common, which means that R intersect S is not the empty set. This isn't always the case. If we perform R natural join S and they have no common attributes, that means R intersect S is going to be the empty set, and the result of a natural join for which there are no common attributes between R and S, that's just going to be the Cartesian product. Okay, enough blabbering on. You want to see an example? Of course you do. You want this to make sense to you, and I'm going to show that by providing an example. So this example is pulled from chapter 3. I just adapted it for use for demonstrating the natural join operation as defined using only relational algebra operations. So R bow tie S is going to be defined using this relational algebra expression. The equivalent query would be something like select star from instructor natural join teaches. We're not going to evaluate this query, we're going to evaluate this query here. So we're going to start inside out by first evaluating the Cartesian join of R and S. So we have the instructor and teacher's relations. We're going to do the Cartesian join, and it's going to have 8 attributes, and that's because instructor relation and teacher's relation. Okay, this is actually wrong. So it's supposed to be 9 attributes. 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah, this slide has an error. It's supposed to be 9 attributes. And it's going to feature every attribute in the instructor relation combined in every possible way with the attribute. It's going to feature the tuples of the instructor relation combined in every possible way with tuples in the teacher's relation. So this has like nearly 200 rows because, let's go back. This one has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Whatever 12 times 15 is, that is how many rows this table has. So this is Cartesian product of instructor and teaches. And much like the first time we've seen Cartesian join, it's going to combine tuples without any regard as to whether they make sense. So Srinivasan does not teach music or physics, only computer science classes. So let's look at the sigma here. We want a way to filter out all these nonsensical tuples, but we don't have the where clause. We have sigma. So this predicate for sigma selects tuples for which the attributes r.ai is the same as s.ai for all I. However, we have a special case here. This is the special case for which there is only one attribute in common. In other words, all you gotta do is simplify our predicate like that. So we just have to find we have to select for the rows for which the instructor ID is the same as teacher's ID. It's starting to become a lot easier now, isn't it? So, this is just the general case for n common attributes, but we're dealing with a special case of one common attribute, which is easier to conceptualize, but keep in mind that in a general case it's going to be n common attributes. There's no reason for us to be restricted to just one common attribute, but we're dealing with the case of one common attribute. So, we have this Cartesian product, and we want to select all the rows for which instructor ID equals teacher's ID. In the previous set of slides where I first demonstrated it, I just crossed out all the nonsensical rows. Rather, instead of that, I'm gonna use arrows to point to the rows that we're going to select. Okay, now we have selected all the rows for which instructor ID equals teacher's ID. Now we have to evaluate pi. So big R union big S. That is just the set of all attributes in relations R and S without duplicates. So we have two ID attributes, and R union S is the set of all attributes between R and S without duplicates. In other words, we're just going to select all the attributes, but we're only going to select one of the ID attributes. And I'm just going to arbitrarily select the first ID attribute here. And now, we're almost there. All we got to do is proceed to the next slide, see it shrink away, and there we go. We have to find our natural join S. So this is natural join defined using only the fundamental operations of relational algebra. It uses pi, sigma, and Cartesian join. Now that we have it, we can add it to our toolbox of relational algebra operations. Once again, this does not make relational algebra any more powerful, it just makes it easier to work with. A few properties of natural join: it's commutative and associative. Order doesn't matter, grouping does not matter. It also means that these two expressions are the same. There's also a variant of natural join called theta join. I'll leave it to you to look that up in the book. Oftentimes, when we perform algorithms or programming, it's convenient to store intermediate results in a temporary value. But for this to work, we need to define an assignment operation. So the assignment operation is a left-pointing arrow. On the left-hand side is the name of the temporary relation. On the right-hand side is an expression. So we can define a temporary relation, temp1, as and assign it the value of, I think this is an error in the textbook. That should be little r, Cartesian product, little s. So that should be the Cartesian product of relations R and S, not their attribute sets R and S. So yeah, that's an error in the book right there. We call that relation temp1, and then we pass that into sigma with this big long predicate R dot A1 equals S dot A1 and dot 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 and R dot AN equals S dot AN of temp1. We call that temp2, and we define our result as being pi sub R union S of temp2. So it turns out this is the definition of a natural join, but we get to define temporary relations along the way. These temporary relations on the left-hand side here, also I think this is supposed to be an arrow, unless this is supposed to be our result. The temporary relation that we define this way, temp1 and temp2, they are not part of our database. So any changes we make to those changes are not committed to the database. It's only when we assign a value to an actual database's relation is when we make these changes. Once again, this does not make relational algebra any more powerful. It just makes it easier to express more complex queries with. Speaking of complexity, how about outer join? So this is an operation that we saw back in chapter 4 when we tried to find class information for every student. But if a student has it, okay, so the query that we had that first demonstrated outer join was a query that tried to find the list of all classes that every student has ever taken. It was a natural join of class information and students' grades. But if a student has yet to take any classes, they won't show up in one of the relations, and if we do the natural join of that, we get missing students. It turns out that if we did the natural join of instructor and teachers here, we get a similar situation. Do you see instructors here that appear in the instructor relation that do not appear in the teacher's relation? Well, I'll tell you right now, there are such instructors. Gold. Yeah, instructor Gold, ID 33456, does not appear in the teacher's relation here. Instructor Califieri, ID 58583. Gold appears in the instructor relation but not the teacher's relation. Califieri appears in the instructor relation but not the teacher's relation. And instructor Singh, 76543, this appears in the instructor relation but not the teacher's relation. That means if we did the natural join of these two relations here, we will not get those three instructors in the natural join. Remember, there are three types of outer join, and outer join is a variant. It's a special join operation in which, if there are tuples in one relation that have no corresponding tuple in the other relation, we force add those tuples and pad the missing information with nulls. We want to mimic that using only relational algebra expressions and whatever operations we've also defined along the way. So remember, there are three outer join operations: left outer join, right outer join, and full outer join. They are represented using the bow tie operator with wings on the left, or on the right, or on both sides. So this is the natural join of instructor and teaches, but it's missing those three instructors: Gold, Califieri, and Singh. If we did instead a outer join, we would get this table instead. So just by looking at this, we can deduce that a outer join is going to be the natural join and the union of this table of missing information. Specifically, what we want in this case is a left outer join, because Gold, Califieri, and Singh appear in the left relation but not the right relation. So we want to do a left outer join, which we can define as the union of the natural join of the two relations and this table down here that we have to add on to. And just like that, we can begin with the definition of a natural join, since we just defined that previously. So, left outer join is, as I said, we can define our left outer join as the union of a natural join plus this missing information. If we can figure out what that missing information is, we can define it, and then we can define our left outer join. So we have these three relations: instructor, teaches, and the natural join of those two. What if we did this? Pi of sub big R, and we pass in R natural join S. R natural join S, it's this table down here. But big R, that is the set of all attributes in relation R. So big R in this case is going to be, okay, so little r in this case represents the instructor relation, so big R represents the attributes ID, name, department name, and salary. If we're gonna project just those four attributes from the natural join of R and S, we're basically doing this. So pi sub ID, name, department name, and salary, we pass in the natural join of instructor in section. So what if we did this? Well, the result is this table. So this is the instructor relation, and this is the projection of the natural join. Oh, by the way, I said previously that sets do not allow duplicates, and that is part of the definition of a set. We have a few duplicates here, so we actually need to simplify this a little further. I'm also going to simplify the subscript text here, so that big I represents the set of attributes in the instructor relation. So big I is just a stand-in for ID, name, department name, and salary. So what does this table mean? Well, look. We have Sir Vassan, Wu, Mozart, Einstein, El Said. We don't have Gold, or Califari, or Singh. So this relation is all the instructors that appear in the natural join, but we don't have the instructors that are left out in the natural join. For that, we need to do this. We're going to do a set difference between instructor and this. If we do that, now we have all the instructors who are missing from a natural join. Alright, let's recap. This is the natural join, and it's missing these instructors. We want to add these rows to our natural join by using the union operation. It means this is the table we want to find that we want to union with the natural join. It means we just need this, because once again, sets disallow duplicates. So what operation do we need to do with this and this such that we get this? What operation lets us combine tuples this way? The answer is Cartesian product. And there is a special case of Cartesian product in which one of the relations has exactly one tuple, one row. Basically, you just take the other table and just concatenate its tuples with a copy of just the one tuple. So if we did the Cartesian join of this relation, which is the missing instructors in our natural join, with this relation full of nulls, we would then get this relation. In the general case, the lower table here, this table full of nulls, that is a constant relation consisting of null values, and the schema of that is going to be the attributes that appear in S, but not R. So these are the attributes that appear in S, but not R. So the common attribute between R and S is the ID attribute. These are the attributes of S, but we don't include the ID attribute because that's already part of one of the other relations. So this is going to be the set of attributes big S minus big R. we do our Cartesian product of these two, and now we have it. We have the definition of an outer join. So it's natural join, I put an extra parenthesis that I shouldn't have done here, union this Cartesian product, where one relation is instructor minus pi sub I of instructor natural join selection, and this constant relation full of nulls. And right down here, that's the definition of outer join. The definition here, this is for left outer join. Right outer join follows similar reasoning. And once we have the definition of both left outer join and right outer join, we can union those two and get the definition of full outer join. This isn't, what I'm gonna say is not homework, but I'm gonna leave it to you to think about. Find the definition of a right outer join, and then use that and the definition of a left outer join to find the definition of a full outer join. So now we have several more operations that we can use in addition to the relational algebra operations, the 6 fundamental ones. There are several more that we would like to talk about. So we looked at the 6 fundamental operations: select, project, rename, set union, set difference, and Cartesian product. And then we looked at additional operations: set intersection, natural join, and left, right, and full outer join. The last ones make up a set of operations that make up something called extended relational algebra. So this is an extension to relational algebra. So I made a little bit of a lie. Relational algebra can express every query that we can think of, but it requires a few extensions for us to achieve that. The first one is generalized projection. Previously, we saw a query in which we multiplied one of the attributes by a constant. That was the query that showed what it would look like if we applied a 10% raise to all of our instructors. Generalized projection is a variant of projection that allows us to do exactly that. So, generalized projection, for example, lets us do stuff like this. We divide salary by 12, and we get a table representing every instructor's monthly salary. There's another operation called aggregation that we denote using this fancy looking G called calligraphic G. This one finds the sum of every instructor's salary. Aggregation also has the distinct keyword, so too does this aggregation in extended relational algebra. So this query says, find the total number of unique instructors who teach during spring 2010. So G sub count distinct of ID of this query here, sigma sub semester equals spring and year equals 2010 teaches. Find the total number of unique instructors who teach during spring 2010. Also, there are cases where we would like to group attributes and perform operations on these groups, not in individual tuples. Once again, we can also do that using aggregation. So this query says, find the average salary of each department. Department name G average salary of instructor. So we group tuples by department name, find the averages of these groups for the instructor relation. So this is aggregation. This represents more complex queries that we saw in, I believe it's the later half of chapter 3. So, I lied when I said that relational algebra can express every query that we can think of. Turns out it takes a few extensions to relational algebra that allows us to do that. But there we go. We have aggregation, we have and generalized projection. Generalized projection lets us multiply attributes like this. Aggregation represents operations such as count and average. A note on duplicates. By definition, a set does not allow duplicates. In SQL, we can allow or disallow duplicates of tuples based on the presence of the distinct keyword. But the definition of a set disallows duplicates. If we want duplicates, we must extend relational algebra to multi-set relational algebra. So this is a variant of relational algebra, except the sets we're dealing with are now multi-sets. They allow duplicates. Just more information about this in chapter 6, page 238. And another thing, we can't do subqueries in relational algebra. Or at least there's no straightforward way to express a subquery using relational algebra. There are further extensions, but they are beyond the scope of the book. The rest of chapter 6 is all about relational calculus. There are two calculus here, much like how in calculus you have 2 or 3 calculuses. Integral calculus, which is actually the second one, differential calculus, which is actually the first one, and maybe vector calculus if you're lucky. So there are two calculuses. Tuple relational calculus and domain relational calculus. This is considered advanced material, so we're not gonna look at it here. The text says they are both inappropriate for casual users of a database system, but they form the basis of other user-friendly languages, QBE and Datalog. It's there if you wanna read up on it. I'm only gonna go as far as relational algebra, however. But if you want a quick summary of what relational calculus even is, it's a declarative or non-procedural query language for relational databases. It specifies a declarative way of how to get data. What to get, but not how to get it. So yeah, that's going to be it on chapter 6. Now I have to talk about your midterm project. So yeah, your midterm's coming out a little bit late, but that's because I had to do other things for other classes. So, you have the option to work with a partner for this. With a partner of your choosing or working alone, decide on an enterprise for which you will design a database. You're going to describe what this enterprise is in a few short sentences. So for example, maybe you want to create your own database for a trading card game. So such a database might focus on multiple TCGs like Pokemon, Lorcana, Magic the Gathering, or you might focus on one specific TCG. Either way, you might have databases on cards from different sets. Like right now, Magic the Gathering has this Spider-Man set, and upcoming is the Avatar The Last Airbender set. Those are considered different sets that you might want to represent in a database. You might also want to represent card membership of a set. There's like a million different variants of Sol Ring now. So it would belong to so many different sets. So that is a card to set relationship that you also want to represent in this kind of database. So you have a card entity and a card set entity and a card membership relationship. So Sol Ring is one of many cards in Magic the Gathering, but it's been reprinted so many times that it's basically a common staple in many Magic the Gathering decks. And you'll find it everywhere, basically. Other information that you would also like to include is information on people's individual collections. Or, other information you'd like to include is the condition and rarity and value of each card. Or maybe this is a database for representing deck lists. So, in Magic the Gathering, people like to come up with deck lists, and that could be information that you would also want to represent in a trading card database. Maybe someone submits a deck list for a Magic the Gathering deck that encodes the operation of a Turing machine. This is real, by the way, look it up. So this is just one of many applications you can write a database for. Other applications include a bookstore database so you can keep track of inventory and people's orders. Another one is a ticket booking system so you can keep track of events if these are tickets for events at venues, or the other definition of a ticket in this context would be airline reservations. So this would be tickets, airline reservations. You'd have a database full of airlines and then a database full of people's reservations. There'd need to be some relationship between seats and planes and whatnot. There is another definition of ticket here, and that is in the context of parking violations. So you can make a parking citation database. This would be a database for currently outstanding violations, who did what violations, what vehicles were involved in the violations, and appeals. If you also include appeals, you would include information about the status of the appeal. And here, the fifth example that I put here is a database for video games. This would track games, players, platforms, and maybe game sales. This database would include information about titles, genres, release dates, and ratings, both in the sense of like rated E for everyone, but also customer reviews ranging from like 1 to 5 stars. So you would have a table of customer ratings, customer name, game name, review, and rating. You would include that information. Okay, so this part 1 is just a description of what enterprise you would like to make a database for. It doesn't have to be any of these, it could be something else entirely. So you can use any one of these to get started, or you might want to pick out a different enterprise. So that's part 1. Part 2, you're going to make an ER diagram of your chosen enterprise, have at least 6 to 8 entities at minimum, and 4 to 6 relationships at minimum. Of course, you must denote your primary keys by underlining them, and you must have your cardinality clearly labeled. If your cardinalities are simple enough that you can get away with arrows, then use the arrows. For consistency, follow the conventions as described in the book. There is an alternate way to denote an ER diagram for an entity where attributes are enclosed in ovals. You can do that, but personally I think it's a little bit more complicated when you could just list out all the attributes in the same rectangle. So for convenience, just go with this notation. It's a little bit neater this way. Although you can represent attributes in ovals, the closest thing you'd have to do for that would have to be something like a relationship that has extra attributes. So what I'm saying is don't put your attributes in separate shapes unless it's for a relationship. When listing attributes for an entity, just put it in the same rectangle as the entity itself. So that's part 2, and that's 40 points. Part 3 is turning that diagram into a set of schemas. Keep in mind that when you have relationships in an ER diagram, oftentimes they're just going to be combined with an entity. We've seen, for example, how the instructor entity has an ID, name, and salary, but an instructor might be a member of more than one department, which we represented using the instructor department relationship here. The thing is, using the rules of simplifying an ER diagram's corresponding schemas, we just ended up merging the department name attribute of instructor department with instructor itself. So what I'm saying is, when you convert your ER diagram into a set of equivalent schemas, chances are many of your relationships are just going to be combined with one of the 2 participating entity sets. So if your ER diagram has, for example, 8 entities and 4 relationships, you would think you'd need 12 schemas, but chances are you probably only need as little as 8. And those are just the ones for the entities, but we combined the relationship attributes with those entities. This is contingent on your first homework assignment as well. If anything, this is just another instance of homework 1, except you are making a diagram for an actual enterprise, all on your own. So the schemas, I've also added a few example schemas, but you're gonna need way more than these. So these are example schemas for the 5 examples that I gave up here, but you are going to need like way more than these. So these are just the quick trading card set, and player, but I did not write it the same way for player collection. I described what attributes you would need to include, but not what they should be explicitly. Oh, by the way, just in case you can't properly underline your anything, just add PK for primary key or FK for your foreign key. So, for example, I did not underline any of the attributes here because they just disappear with a red underline squiggly here. So card ID would be the primary key for a trading card. Set ID is a foreign key, which appears in trading card set. The trading card set has a set ID, but it's the primary key for trading card set. It's a foreign key for set ID, which is a part of trading card. There's that concept of referential integrity again. A card must belong to a set that also exists. Soul Ring appears in lots of sets, for example. So your criteria is going to be graded on completeness and correctness. Does it represent your enterprise accurately? And does your diagram fit the conventions that it described? I might deduct points if elements are missing or labels are missing. But anyway, that is your midterm. Once again, it's coming a little bit late, but you have by this time you have a little less than 2 weeks to complete it. But yeah, that's your midterm right there. You're going to make your own ER diagram. You may look at other diagrams for reference, and I'm not gonna stop you from looking at other diagrams for reference. It's just that there are also other reference diagrams in here. Just that once you have the basics of how to create an ER diagram, you're already halfway there to creating the tables in your database. So what's not included in these instructions is you do not have to write the commands for creating a table. Not yet, at least. You can, though. You don't need to show your schemas as a set of create table commands. That's for the final. If you do, just screenshot those commands. Otherwise, you can just list out your schemas like that. And that's your midterm. Find an enterprise for which you would like to make a database. Describe that enterprise. Create an ER diagram, and then create a set of schemas from that diagram. You are allowed to work with a partner for this, or you can work alone. I have Canvas set up so that you can self-sign up for your own groups, but just in case you have any issues with that, we can talk about it next class or during office hours, okay? Alright, that's gonna be it for this video. Good luck on your midterm assignment, and yeah, we'll pick it up from here next week.